Okay, for today's deep dive, we have a huge stack of research on a topic that I think most people get wrong.
You mean the history of robotics?
Exactly. When you look at the sources, everyone wants to start in, the 1960s with some industrial arm,
Right, but if you do that, you miss... Well, you made the entire first act of this
a
story.
really long first act.
Yeah. The sources make this crucial distinction. There's the era of automata, which was all about mechanical curiosity, sort of mimicking the form of life,
And then the era of robotics, which is more about function, autonomy.
and eventually mimicking the mind.
So that's our mission today. We want to trace how we got from, believe it or not, steam-powered birds in ancient Greece to the debates we're having now about machines holding human consciousness.
And that early history is just, it's shockingly sophisticated.
It really is. I mean, where do we even start?
You have to start with Archytas of Tarentum, around 350 BC. He builds this wooden pigeon,
Right.
and it's powered by a jet of steam. It actually flew. It wasn't just a toy. It was, a genuine study in aerodynamics.
The first rocket-propelled flight, basically. But the one piece of engineering that just blows my mind is Al-Jazari.
Oh, yeah. In 1206 AD.
We think of programmable as a 20th century word, but he built a boat with 4 mechanical musicians.
And you could change the rhythm they played?
How did he even do that?
That's the key. He used a camshaft with these movable pegs. So by physically moving the pegs, you reprogrammed the drum sequence.
It's the mechanical ancestor to the punch card.
It is. Which brings us to Da Vinci, in 1495. His mechanical knight wasn't just for show.
No, it was an anatomical study. He used cables and pulleys to mimic how muscles work.
And that whole obsession with mimicry, it sort of peaked with the Jacques-Hédros brothers in the 1770s.
Oh, their writer automaton.
Thousands of parts. It could dip a quill in ink and write out custom text, but for all that complexity, they were still just automata.
They were just scripted loops. They couldn't react.
Exactly. They couldn't react to the world.
Which is what makes the next shift so interesting. The sources all highlight that the move from automaton to robot wasn't an engineering leap.
No, it was a fictional one. It came from Karel Oppek's play in 1920.
RUR,
Yeah, where he coined the term from the Czech word robota,
which means forced labor.
or serfdom. And that's a huge moment. It reframes the machine from a curiosity into a worker.
And that fictional frame then dictates reality. You had Asimov in 1942 creating his 3 laws to put ethical guardrails on these workers before they even really exist.
But when the hardware finally catches up in 1961 with Unimate, the reality was much more simple.
Unimate at GM, the first industrial robot.
Right. But it was still blind. It was just moving these hot die castings. A dangerous job, for sure. But it was just repeating coordinates. If you moved the part an inch, Unimate would miss it.
And that's why Shaky, in 1972, is probably the bigger leap in the timeline.
For sure. That's the jump from pure repetition to reasoning.
The closed feedback loop.
Exactly. Shaky had cameras, bump sensors. It could see a room, perceive an obstacle, and then figure out a new path. It broke the script.
So then, moving into the modern era, that autonomy starts to leave the factory.
And come into our homes. We get Roomba in 2002, which normalized the idea of a robot just roaming around your space.
But on the industrial side, you get the rise of cobots.
Collaborative robots, which is a huge safety revolution. Old robots needed cages, they'd crush you.
Right.
Cobots can feel an impact and stop. It finally let humans and droids work side by side.
But right now, we're in what the research is calling Generation 5. We're moving away from hard-coding every little movement.
And into the world of LLMs and deep learning. It's a total paradigm shift.
So instead of coding move arm 45 degrees, what do we do now?
You give it a goal. You might show it a video of the task or just tell it, clean up that spill, and it figures out the physical actions required.
It's learning through trial and error, just like a person.
And that's where the future starts to get really blurry. We're not just improving the software anymore, we're integrating it with biology.
You're talking about things like Neuralink, brain-machine interfaces.
Yeah, we're turning robotic limbs into basically extensions of the human nervous system. We've gone from Al-Jazari's pegs on a camshaft
To potentially uploading our own neural patterns into a machine.
It completely changes the fundamental question. It used to be, can a machine do what a human does?
And now?
Now, with the real possibility of preserving consciousness in these things, the question becomes, at what point is it no longer a machine?
Right. If a robot holds your memories, your personality, your decision-making, is it just a tool or is it you?
That's the big one.
Something to think about. Thanks for diving in with us.
So, looking through all this research, I have to say it felt less like a scientific review and more like the script for a sci-fi movie.
I get that. On one hand, you have machines that are essentially breeding themselves.
Right. And on the other, you have this idea that the exact same technology could, stop human aging for good.
It seems like two completely separate tracks, but the sources draw a surprisingly straight line between them. It all comes down to Darwinian evolution.
Survival of the fittest.
But for code, yeah.
Okay, so I think our mission here is to trace that line. We need to get from like a simple industrial arm in a car factory to this concept of substrate independence, which is a lot to wrap your head around.
Definitely.
So let's start with the robots. The biggest thing that jumped out at me was that humans aren't really in the driver's seat anymore. We're not designing these things.
Not in the old way, no. This is the whole field of evolutionary robotics. So instead of an engineer coding every single movement, the new way uses a genotype to phenotype process.
Which is just fancy biology talk for code becomes a body.
Exactly. The code is the DNA.
Mm-hmm.
A simulation just generates a bunch of random robot bodies and tests them. If a design immediately falls over, it gets deleted.
And if it manages to walk a little bit further.
It survives. It's fitter.
And this is the wild part. The survivors then get to, I guess, have sex.
Digitally, yeah. The system takes the code from the best ones, mixes it all up through what they call mutation and crossover, and then it spawns a whole new generation.
And because a computer has no human bias, no idea what a robot should look like, you get these bizarre forms. The sources called them alien-like.
Well, human engineers love symmetry and logic. Evolution only cares about what works.
And this process has moved so fast. We went from the Unimate arm at GM in 1956.
Which was basically just a dumb crane.
To Carl Sims's virtual creatures in the 90s, and now we're at a point where these evolved designs are actually being 3D printed.
Fifth generation autonomous robots.
Okay, so we've established that algorithms can design better physical bodies than we can. And this is where the research makes the jump, applying that same idea to our bodies.
That's the bridge. The sources break down the path to immortality into three clear phases: repair, upgrade, and then transfer.
Repair feels the most grounded, like something we can actually imagine happening soon. It's about extending the warranty, right?
Think of it as high-tech maintenance. The research talks about nanobots clearing plaque from arteries or hunting down cancer cells.
And bioprinting, printing entire organs using your own cells so there's no rejection.
Exactly. But then you get to phase two, upgrade. And that's a whole different game.
That's cybernetic augmentation. You stop fixing the broken biological parts.
And you just replace them with superior robotic ones. But the critical piece here is the brain-computer interface, the BCI.
Like Neuralink, hooking your brain up to the cloud to expand your memory or processing speed.
But even with all those upgrades, the sources are pretty clear. The biological brain, the wetware, it eventually fails. Entropy wins.
Which forces us into the final phase, phase 3, transfer.
And this is where that term substrate independence finally comes into play.
It sounds incredibly complex, but the idea itself is kind of simple. The software of your mind doesn't have to run on the hardware of your brain.
Right. It could run on silicon.
Yeah.
The goal is whole brain emulation. You map every single neural connection, the entire connectome, and you upload it.
Once it's uploaded, you can then download that consciousness into a robotic avatar.
Your mind becomes code. You can still interact with the physical world, but you're no longer biological. And the research suggests that agentic AI might help us solve the final pieces of that puzzle by 2030.
So just to recap this whole journey, we started with humans coding simple robots. Then we let robots evolve themselves. And now the final step is to use that same technology to evolve ourselves completely out of our biological bodies.
That's the trajectory. But it leaves us with a massive, massive philosophical question about identity.
And that's the thought I really want to leave you with. If we actually pull this off, this transfer, and you upload your consciousness into an avatar, is it really you in there? Or have you just created a perfect digital copy that gets to live forever while the original you quietly fades away? So the stack of research we're looking at today, it completely reframes this whole concept of immortality.
It really does.
Yeah.
The main argument here isn't about, some fountain of youth.
No, not at all. The sources are framing living forever as a strict engineering challenge.
It's a massive shift in perspective. We're moving from the biological question of if we can extend life to the engineering question of how. And this roadmap, it's not vague. It outlines a pretty specific three-phase rollout.
Yeah, the robotic future, it reads like a software update schedule. You have biological maintenance, then the cyborg transition, and then finally the synthetic dawn.
Exactly.
So let's start with what's coming up first. The 2030s, biological maintenance.
Right. And this phase is all about optimization. We aren't replacing the body yet, we're just aggressively maintaining it. The sources lean heavily on Ray Kurzweil's work here.
And the big prediction is the medical nanobots, right?
In the bloodstream.
That's the one. But we should be clear, these aren't like tiny surgeons floating around.
No, it's more like a supplemental immune system. Precisely. It's programmable immunity. The literature describes them identifying and destroying cancer cells on site, or even clearing plaque from your arteries.
So it's hardware. And then there's the software patch. The sources get into using robotics-assisted CRISPR to kind of edit out the aging process.
That's the patching idea.
Yeah.
Instead of letting errors build up in your DNA, which is basically what aging is, you use gene therapy to fix the code.
So you're just in constant maintenance mode.
Constant maintenance. But then the 2040s, that's where the strategy shifts. From fixing to upgrading.
Phase 2, the cyborg transition. And this is where that definition of human starts to get really blurry.
It does, because the argument is that our biological organs are basically legacy hardware.
Yeah.
They fail.
They wear out.
And they're inefficient. So in this phase, if your heart fails, you don't get a donor heart. You install a robotic one that, never gets tired.
But the most critical upgrade mentioned isn't the heart or the lungs, it's the neural lace.
The advanced brain-computer interfaces.
Yeah. And we're talking way beyond just controlling a mouse with your mind, which is already happening. This is about bandwidth.
Bandwidth is the bottleneck. To really merge with AI, you need a high-speed connection, a direct link between your cortex and the cloud.
Which would let you export the data of you in real time.
And that creates, essentially, a continuous digital backup of your memories, your thoughts, your personality.
So if your biological brain is destroyed, the data is fine. Your mind is preserved.
Which sets the stage perfectly for the post-2050 era, the synthetic dawn. This is all about what they call substrate independence.
That term comes up so much, it basically means your mind is software. And software doesn't care what hardware it runs on, right?
That's the aha moment. It can run on meat, or it can run on silicon.
So once you map the connectome, the full wiring diagram of your brain and upload it, you're not tied to your body anymore.
You're not. You could inhabit a robotic avatar, a humanoid one for, say, walking around on Earth.
Or a hardened probe for exploring deep space. Your body just becomes an accessory.
And it completely redefines death. Death is no longer a biological event. It's a data loss event.
A server crash.
Exactly. As long as you have backups, you persist.
But this is where the engineering answers the how, but kind of ignores the who. There's a huge philosophical problem here that the sources raise, the copy problem.
Right. If I upload my mind to a machine, is that me in there? Or did I just create a perfect digital clone of me while the original me still grows old and dies?
It's the difference between moving a file and copying a file. It's fundamental. And then there's the access question. Is this a human right?
Or does immortality just become the ultimate luxury good?
You could end up with a literal caste system, the biological mortals and the digital immortals.
A very real risk. And then there's the question of purpose. Scarcity creates value. If time is no longer scarce, do we lose that urgency? The thing that fuels art and innovation?
Did we just get bored?
It's the ultimate trade-off, isn't it? We might gain eternity, but lose the very friction that makes being human meaningful.
So we've gone from nanobots cleaning our arteries all the way to uploading our consciousness to the cloud. It's a total restructuring of what it means to exist.
It turns human evolution from a natural process into a design project.
Before we wrap up, I want to leave you with a thought to chew on. It's a variation of the old ship of Theseus paradox.
Okay.
If you follow this roadmap and you slowly replace every biological part of yourself with a machine, piece by piece over 30 years, at exactly which specific update do you stop being human?
That is the question.
Thanks for diving in with us.